All right, so let's talk a little bit about exponential functions. Exponential functions probably are one of the more applicable things in the real world. Anything that grows by a percentage uses exponential functions. And so as I just said, exponential functions grow by a given percentage. Examples of this are any kind of population growth, banks, money, loans, all that stuff is done by percentage. The general form of it looks like this: y equals a times b to the x, right? So in other words, like this: y equals a times b, and then this is in the exponent spot, thus the name exponential, where a is the start amount, similar to the y-intercept. And that makes sense, right? Because if b is 0, if x is 0, then anything to the 0 power equals 1, so this equals a times 1. So it is the same. So when my x-coordinate is 0, this will be the y-coordinate of my point, or my y-intercept. And so a is the start amount, or y-intercept, and b is the constant ratio. And we'll talk more about that later. You also might see it in the world kind of like this. And you can see that that looks pretty much identical. It's just this little 1 plus r bit, right? So we've got a times 1 plus r to the x, and a times b to the x. So b equals 1 plus r. Now what's r? Well, a is still the start amount, and r is the percent growth, or the rate. Now, let's talk about, just in general, how we use these numbers, b and r. So, given any value of b, given any value of a, we can find the percent change by finding the difference between b and 1. So let's go down here and look at some examples. So let's say we have this example here. Y equals 5 times 1.25 to the x. This represents a 25% increase, right? Because if you think about it, right, 1 plus r equals b. So if I'm trying to find that percent change, or that r, I'm just going to subtract 1 from both sides, and I'm going to get r equals b minus 1. So let's take this one. So I have, if my b is 1.25, and I subtract 1 from both sides, right, then I'm going to have a 0.25 is going to be that rate of change. Now that's pretty easy when it's like these two, right? This is a 75% increase because r is 0.75, right? Now, but it gets a little bit trickier when you guys look at this one. Now, 1 plus r equals 0.95, right? And so if I take 0.95 and I'm solving for r and I subtract 1, then all of a sudden I get a negative 0.05% rate, which is a 5% rate change, or 5% decrease. That's a 5, not a 2. Sorry about that. And this one, for example, is a 25% decrease, because 0.75 minus 1 equals negative 0.25, or a 25% decrease. So given any value of b, if we subtract 1 from it, that's going to give us that percent change. In other words, how much that function is changing. Now, let's kind of create a function here based on some real-world data. So this is an article that came out yesterday in Reuters, which is a business magazine. The U.S. economy slows in fourth quarter, but the growth outlook still looks favorable. U.S. economic growth braked more sharply than initially thought in the fourth quarter amid slow-paced stock accumulations by business and wider trade deficit. Blah, 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 blah. The gross domestic product expanded by 2.2% annual pace, revised down from the 2.6% estimated last month. So in other words, that doesn't seem very different just by looking at it. Okay? And if we were to write this equation, right? Now, I happen to have researched that the U.S. GDP was $15 trillion. Okay? So that would be my start amount. And we're going to predict what's going to happen to the gross domestic product is going to be in a few months. So let's write it this way. We'll say G of X, and in this case, X will be years. X is years. Okay. So we have our start amount, 15 times 1 plus, let's turn this into a percentage point, so 2.2% as a decimal will be 0.022. So we'll say plus 0.022 to the x. So that's my equation that represents that function, that one. And then this is the other one. Let's call it predicted of x equals same start amount to the x. Okay. Now let's have a little fun with our calculators here, and let's see how big a difference this is and what this means. Even that small of a difference. Turn the calculator on. Now here are my two equations, right, that I typed in, and just for fun I'll type them in again, right? So I'm going to say 15 so 15 times 1 plus r in this case is going to be 1.022, and then the to the key is right here, and then the variable key is right here, to the x. Okay, so now I have both of my equations in here. Now, this one, the y-intercept is 15, so my y value, so when I think about my window, it doesn't need to be, y doesn't need to be very big just yet. So I'm going to go from 1 to 10 for x, and then from 10 to 30 for y with scales of 1. And let's look at the graph real quick. So here's the 22% or 2.2% increase graph coming along. Kind of looks like a line, doesn't it, at this point? And you can see the 2.5 just squeaking right above it, right? And that doesn't seem that big of a difference. Let's look at the table so we can actually see the difference, right? Let's start at 0 and go up by 1s. Back to my table. Okay, so you can see after 1 year the difference isn't that great, right? Just, you know, what's that going to be? We'll say $40 billion difference, right? Not that big a deal. And then we can see up in here we're starting to get into $100 billion difference-ish, right? This one's getting a little bit bigger. And this one's $300 billion difference more, okay? Not that big of a deal. Now, but when you think about all of a sudden, so when you think about it as 17 trillion and you realize the difference of 300 billion is several large companies' difference. And that makes a big difference. But now the real power of exponential growth lies in when we run these out a little bit. So let's say that this kept up for 30 years, okay? And I'm going to give myself a little bit of room to work. And let's see what the difference in the two graphs is. You can see it coming along there. And 2's kind of coming along. And you can't see that very well. Let's change my window values real quick. Oh, come on. Let's change that to 50 so you can see it better. you should notice that eventually we get to a point where there is a considerable difference. And one of them will actually, if you run it out long enough, they'll actually double each other a lot quicker. Okay? All right, let's keep moving along. So even a 0.4% difference can make a big difference in the long run. All right, here we go. Most automobiles depreciate as they get older. So suppose an automobile that originally costs $14,000 depreciates by 20% each year. So let's write that function. Let's call it A of x. Okay. So my start amount is going to be $14,000, and we're going to multiply that times 1 minus 0.2 to the x, because depreciates means goes down by 20% each year. And that's equivalent to 14,000 times 0.8 to the x. Okay? These two things are the same. That's how we write that equation. So what is the value after 2 years? Well, I can go into my calculator, right? And I can just type that equation in just like that. I can say 14,000 times, and I can either use the parentheses, 1 minus 0.2 to the x, or no, to the 2, because I want 2.5. I want 2.5 years. We could represent it like this. 2.5 equals 14,000 times 1 minus 0.2 to the 2.5, right? So 2.5 years. And we get that the value of the car at that point is approximately $8,014.07. Okay. Now, when will it be worth half its initial value? Well, half of its initial value is $7,000, right? So, what I want you guys to do right now is guess and check around and see what you guys come up with. For example, I'm going to go 14,000 times, let's see, so it dropped to that level. So I'm going to try 3.8 to the third. You can see I'm getting close there. So why don't you guys guess and check around a little bit, and I'll reset the video here.